Look at your hands. Turn them over. See the fine lines, the map of a life etched into the skin. You think you know what they are. You believe they are solid. You trust in their substance, in the reliable fact of their presence. You move them, and the world obeys. This is the first and most fundamental truth of your experience. The world is solid. The world is real. The world is there. But this is a story our senses tell us to keep us sane. It is a comfortable illusion, a necessary simplification for creatures who must navigate a landscape of causes and effects. Because beneath the skin, beyond the cells, past the atoms themselves, lies a reality of such profound strangeness that it borders on the unbelievable. A reality built not on things, but on rules. Not on substance, but on mathematics. Not on certainties, but on probabilities. And in the deepest corners of this reality, at the very edge of our understanding, physics has long told us there is a place where the story ends. A place where the rules break down completely. A point of no return not just for matter, but for meaning itself. They call it the singularity. For over half a century, it has been a settled fact. A ghost in the machine of the cosmos. An accepted piece of the grand architecture. It is the destination at the heart of every black hole. An infinitesimal point of infinite density. A place where space and time cease to be space and time and become something else. Something nameless. The singularity is the accepted ending. The cosmic cul-de-sac. The full stop at the end of the universe's longest and most complicated sentence. It is the one place where the elegant equations of Albert Einstein, the very grammar of our universe, scream a nonsensical answer. Infinity. And we have lived with this ghost. We have built our cosmology around it. We have accepted that the universe contains within it the seeds of its own logical destruction. It has been a pillar of our physics, a foundational truth proven by one of the sharpest minds of our time. But what if that pillar is beginning to crack? What if the ghost was never there? What if the most fundamental assumption we have made about the darkest objects in the cosmos is wrong? This is not a question from the fringes of science. It comes from the very heart of the establishment. It comes from a mind that knows black holes more intimately than almost any other. A quiet challenge has been issued, a mathematical gauntlet thrown down, suggesting that the singularity, this point of infinite madness, may be nothing more than a mathematical illusion, a trick of the light. To understand the depth of this rebellion, you must first understand the illusion it seeks to shatter. You must first accept the lie. The lie is not that the world is solid. That is a simple, harmless deception of scale. The far greater lie, the one physics has told itself for decades, is that the universe is required to have a breaking point. The common perception, the one you likely hold, is of a black hole as a cosmic vacuum cleaner, a monster that eats light. This is true, in a way, but the reality is more elegant and more terrifying. A black hole is not an object in space. A black hole is a place. It is a region of space-time so warped, so violently curved by gravity, that it has turned in on itself. Imagine space-time as a flowing river. Everywhere else in the universe, you can swim against the current. You might be slow, but you can make progress. But at a certain line, the event horizon, the river of space-time itself, is flowing inward faster than the speed of light. Nothing, not even the fastest thing in the universe, can swim fast enough to escape. You're not being pulled by a force. You are being carried by the very fabric of reality, which has itself become a one-way street. This is not speculation. This is the direct consequence of Einstein's theory of general relativity, his masterpiece that describes gravity not as a force, but as the curvature of space-time. And for a long time, physicists hoped that these bizarre predictions, these one-way rivers of reality, were just mathematical quirks, flaws in the equations that would disappear with a more complete understanding. They were too monstrous to be real. But the universe, it seems, has a taste for monsters. To see where the ghost of the singularity was born, we must travel back, not just in space, but in time. The year is 1915. The world is tearing itself apart in the Great War. And in Berlin, a man named Albert Einstein publishes a set of equations that will rewrite our understanding of existence. 10 elegant, beautiful field equations that describe the relationship between matter, energy, and the geometry of space-time. Einstein believed he was describing the gentle, sweeping curves of planetary orbits, the majestic dance of galaxies. His theory was a symphony of cosmic harmony. He did not know that he had also written the score for its most violent and terrifying solo. Section, he was the reluctant father of the idea, a man who found the implications of his own work deeply unsettling. He believed the universe should be stable, eternal, and sensible. His equations, however, had other ideas. The first pioneer to truly confront the beast was Karl Schwarzschild, a German physicist and astronomer, serving on the Russian front in 1915. Amidst the chaos of trench warfare, Schwarzschild found the first exact solution to Einstein's field equations. He was describing the simplest possible scenario, the space-time geometry around a single, non-rotating, spherical mass. What he found was shocking. The solution contained a mathematical feature, a radius at which the equations went haywire, a point of no return, a horizon, and at the very center of this solution, at a radius of 0, the equations exploded. The curvature of space-time became infinite. It was the first glimpse of the singularity, a mathematical monster lurking in the heart of Einstein's beautiful theory. For decades, the scientific community, including Einstein himself, dismissed it. They argued it was an artifact of the perfect symmetry of Schwarzschild's solution. A real star, they reasoned, would be messy, rotating, imperfect. It would not collapse so perfectly to a single point of infinite density. The problem, they hoped, would solve itself. Nature, they assumed, would abhor an infinity. For 50 years, this hope persisted. The black hole remained a theoretical curiosity, a ghost story physicists told each other. Then came the visionary, the man who would prove the ghost was real. The year was 1964. The scientific world was buzzing with the recent discovery of quasars, incredibly bright and distant objects pouring out unimaginable amounts of energy. What would possibly power them? The idea of gravitational collapse, once a fringe theory, was gaining traction. Perhaps these were massive stars collapsing under their own weight, releasing enormous energy. But the old objection remained. What about the collapse itself? Wouldn't the asymmetries and rotation of a real star prevent the formation of that dreaded infinite point? This is where Roger Penrose, a mathematical physicist at the University of Cambridge, entered the stage. He was not a traditional physicist. He was a geometer, a poet of shapes and topology. He thought in terms of forms and structures, not just forces and particles. And he saw a way to ask the question differently. He did not try to calculate the messy details of a collapsing star. Instead, he asked a more fundamental question about the nature of gravity itself, as described by general relativity. He introduced a new mathematical tool, the concept of a trapped surface. Imagine a sphere of light, with flashes being emitted from every point on its surface. Normally, you would expect half the flashes to travel outwards and half to travel inwards. The sphere would expand. But deep inside a powerful gravitational field, Penrose realized you could have a surface where the curvature of space-time is so extreme that even the outward pointing light rays are forced to travel inward. The sphere of light can only shrink. This was the trapped surface, a sphere of light that cannot expand. It is the defining feature of a black hole, a mathematical formalization of the point of no return. And from this simple, elegant idea, Penrose constructed a proof of breathtaking power and generality. In 1965, he published his singularity theorem. It did not matter if the star was rotating or lumpy. It did not matter what it was made of. Penrose proved that if general relativity is correct, and if a trapped surface ever forms, then the formation of a singularity is not just possible. It is inevitable. He did not prove the ghost existed. He proved it had to exist. This was the core paradox that has haunted physics ever since. General relativity, our most successful theory of gravity, a theory that describes the smooth, continuous fabric of the cosmos, logically predicts its own downfall. It proves that there must be places in the universe where its own laws and all the laws of physics come to a sudden and complete stop. The singularity was no longer a quirk of a specific solution. It was a fundamental feature of gravity. The triumph was also a disaster. It meant that physics was, at its heart, incomplete. It pointed to the deep, irreconcilable conflict between the two pillars of modern science: the smooth, geometric world of general relativity and the frenetic, quantized world of quantum mechanics. In the gentle curves of space-time, there was no room for the fuzzy, uncertain nature of the quantum realm. And at the infinite spike of the singularity, there was no room for anything at all. Something had to give. Most physicists assumed that a future theory of quantum gravity would one day fix the singularity, smoothing it out with the uncertainties of quantum mechanics. The infinity, they believed, was just a sign that general relativity was being pushed beyond its limits. But the theorem remained, a mathematical iron cage. Once a trapped surface forms, the journey to the center must end in a singularity. There was no escape. Or was there? To understand the new challenge, we must dive deeper. We must look at the fine print of Penrose's brilliant proof. We must understand the taxonomy of these strange cosmic beasts and the rules they follow. First, there is not just one kind of black hole. The monster found by Schwarzschild was the simplest form: static, uncharged, a perfect sphere of gravitational influence. It was a useful theoretical tool, but not a realistic one. Everything in the universe spins. Stars spin, galaxies spin, and when a star collapses, its spin must be conserved. It spins faster and faster, like an ice skater pulling in their arms. A realistic black hole must be a rotating black hole. Finding the solution for a rotating black hole was a monumental task, a problem that stumped physicists for decades. Then, in 1963, a brilliant and unassuming physicist from New Zealand named Roy Kerr did what no one else could. He found the exact solution: the Kerr metric. It was a far more complex and bizarre reality than Schwarzschild's. A rotating black hole drags space-time around with it, creating a swirling vortex called the ergosphere. Inside this region, you are forced to rotate with the black hole, even if you are outside the event horizon itself. Space-time is no longer static. It is a whirlpool. The Kerr metric was a triumph. It described the black holes we believe actually exist in our universe. But it, too, contained a singularity. A different kind of singularity, not a point, but a ring, a one-dimensional loop of infinite density. But a singularity nonetheless. And Penrose's theorem still applied. The monster had been tamed, given a spin, but its heart was still infinite. This is the landscape. A universe populated by rotating Kerr black holes, each one guaranteed by Penrose's theorem to hide a ring-shaped singularity at its core. This has been the bedrock of astrophysics for 60 years. Now, we must look at the rules of the unseen. How do we know where things go in this warped reality? We follow their paths. In physics, these paths are called geodesics. A geodesic is the straightest possible line through a curved spacetime. It is not always straight in the way you might think. On the curved surface of the Earth, the straightest path between two cities is a great circle, a curve. A geodesic is the path of least resistance, the natural track laid down by gravity. There are two fundamental types of geodesics, two kinds of travelers in the cosmos. There are time-like geodesics, which are the paths followed by anything with mass. You, a planet, a spaceship. You travel through space-time, always moving forward in time, but at a speed less than light. And then there are null geodesics. These are the paths followed by massless particles, by light itself. A photon. It travels at the absolute cosmic speed limit, and for it, time itself does not pass. It experiences its entire journey, from its creation to its absorption in a single instant. It is a perfect, idealized traveler, surfing the very edge of causality. This distinction is subtle, but it is everything. How do we prove things in this abstract, mathematical world? We use the tools at hand. And the simplest, cleanest, most elegant tool to use when probing the structure of space-time is light. Null geodesics. They are pure, uncomplicated by the messiness of mass. Penrose's singularity theorem is a masterpiece of geometric reasoning, and it is built upon the behavior of null geodesics. He used families of light rays, tracing their paths as they fall into the gravitational well. By showing that these light rays, following these idealized null geodesics, must inevitably converge and focus to a point, he proved the existence of the singularity. His proof is a statement about the destiny of light. And we all assume that what was true for light must also be true for matter. If the path of a perfect, massless photon ends in infinity, then surely the path of a clumsy, massive spaceship must end there too. It seemed a safe assumption. It seemed logical. But what if it isn't? This is the heart of the challenge being mounted by the very man who gave us the rotating black hole, Roy Kerr. Now, in his later years, he has revisited the fundamental assumptions, and he has pointed out a flaw. Not a flaw in Penrose's mathematics. The theorem is logically sound. The flaw, Kerr argues, is in its application to physical reality. The proof works for null geodesics. It is a truth about the journey of light. But does anything truly fall into a black hole along a pure, null geodesic? Light does, of course. But what about the collapsing star itself? What about the matter and energy that form the black hole in the first place? That is all matter. It follows time like geodesics. Kerr's argument, laid out in a recent paper, is a quiet earthquake. He suggests that we have been looking at a simplified map and mistaking it for the territory. He argues that the singularity only appears at the end of null geodesics. It is a destination that only light can reach. For a traveler with mass, following a time-like path, the journey may be different. As matter falls inward, it carries its own gravitational field. It changes the very space-time it travels through. The infalling energy, Kerr suggests, could alter the geometry near the center in a crucial way. It might create a kind of gravitational pushback, a blue shift of incoming energy so intense that it prevents the final catastrophic collapse to an infinite point. Imagine the singularity as a perfect, infinitely sharp point of a needle. Penrose's proof shows that if you slide perfectly down the needle's axis, a null geodesic, you will hit that infinite point. But Kerr is suggesting that any real object, following a time-like geodesic, is like a small bead with a hole in it. It is constitutionally incapable of hitting the exact tip. It will always have some slight deviation, some wobble, because of its own mass and energy. And that wobble, amplified by the extreme physics near the center, might be enough to make it miss the point entirely. Instead of a singularity, the matter might pile up at a fantastically high but finite density. It might bounce. It might form some new, exotic state of matter we cannot yet conceive of. But it would not be an infinity. It would not be a place where physics breaks. This is a profound shift in perspective. It suggests the singularity is not a physical place, but a mathematical artifact, a boundary condition of our equations that is never actually reached by the physical process of collapse. It exists in the idealized world of pure light rays, but not in the messy, substantial world of collapsing stars. The experimental evidence we have, the shadows on the wall, do not help us here. Our observations of black holes are magnificent. We have seen the silhouette of the event horizon with the Event Horizon Telescope. We have heard the chirp of gravitational waves as two black holes merge, a sound that perfectly matches the predictions of general relativity for the behavior of space-time far from the center. But all of this evidence confirms the existence of the event horizon. It confirms the reality of these one-way rivers in space-time. It confirms the macrostructure of beast. It tells us nothing absolutely nothing about what lies at its heart. The center is forever causally disconnected from us. We can never receive a signal from it. We are judging the monster by its shadow, but we have never seen its face. And so the debate moves to the realm of pure logic and mathematical physics. It becomes a question of which path is the real one. Let's amplify the paradox. Let us truly sit with the strangeness of what a singularity implies to understand why avoiding it is so important. The singularity, as predicted by classical general relativity, is a violation of everything we hold dear in science. It is a point of absolute unpredictability. If you knew the exact state of every particle falling into a black hole, you still could not predict what happens at the singularity. The laws that govern cause and effect dissolve. Information is destroyed. The past is erased, and the future is unwritten. This is not just a problem for physics. It is a problem for philosophy. It is a problem for the very idea of a rational universe. For the universe to contain a place where logic dies is deeply, profoundly unsettling. It is a cosmic error message printed in the fabric of reality itself. This is the spooky phenomenon at the heart of it all. Not action at a distance, but the end of all action, the end of all distance, the end of time. It is a true boundary to existence. The role of the observer becomes paramount in this new debate. Penrose's proof used an abstract, mathematical observer, a ray of light, an inhuman, timeless traveler. Its journey ends in oblivion. But Kerr insists we must consider a physical observer, a chunk of matter, a real thing. And for that observer, the journey's end might be radically different. The act of falling in, the very substance of the traveler, might change the destination. Think about that. Reality might be shaped not just by the landscape, but by who is walking through it. The path you take could determine whether the abyss at the end of the road is truly bottomless or if it has a floor after all. This is where we must leave the comfortable shores of physics and wade into the deeper waters of philosophy. What does this mean for you? For your understanding of the world? You are built from the dust of collapsed stars. The iron in your blood, the calcium in your bones, were forged in the hearts of stellar furnaces, some of which were massive enough to become black holes. Your physical story is inextricably linked to the story of gravitational collapse. To say that the singularity is an illusion is to rewrite a fundamental chapter of that story. It is to say that the universe is not, after all, programmed to contain these points of failure. It is to say that even in the most extreme circumstances, under the most incredible pressures, the laws of physics might hold. They might bend into shapes we can barely recognize. They might produce states of matter so exotic we have no names for them, but they do not break. If Kerr is right, then the universe is more resilient, more self-consistent than we ever believed. It has a way of avoiding the mathematical traps we set for it. It refuses to compute infinity. This forces us to redefine reality itself. What is a real object in physics? Is it something we can point to? Or is it a concept that is mathematically consistent and makes successful predictions? The singularity was real in the second sense. It was a prediction of a fantastically successful theory. We organized our understanding around it. But if it is an artifact of a specific, idealized way of calculating, then its reality becomes suspect. It becomes a ghost generated by our own tools. It's like finding a dragon on an ancient map. The map was the best tool they had for navigation. It was useful. It was real in its effects. But that doesn't mean the dragon itself was ever a physical creature. It was a symbol of the unknown, a placeholder for here be monsters. Perhaps the singularity is just that. The here be monsters on the map of general relativity. A warning sign that the map is ending and a new kind of territory is about to begin, the territory of quantum gravity. Kerr's argument suggests we might not need to plunge into that unknown territory to solve the problem. The solution might be hidden in the folds of the old map, in a detail we overlooked because we were so dazzled by the simplicity of light. Ask yourself, Is a mathematical proof a discovery of a feature of the universe, or is it an exploration of the logical consequences of our own assumptions? We assumed that the path of light was a sufficient guide. We assumed that the simplified model held the essential truth. That assumption, born of a desire for elegance and calculability, may have led us astray for half a century. This brings us to the most speculative and most profound of leaps. If the universe has these subtle, built-in mechanisms for avoiding infinities, for preventing its own logical breakdown, what else might it be capable of? This line of thought echoes other deep mysteries in physics. The universe seems fine-tuned for existence. Its fundamental constants are exquisitely balanced on a knife's edge, creating a world that allows for complexity, for stars, for planets, for life. Change them by a fraction, and the cosmos would be a sterile, empty void. Is this a clue? Is the avoidance of a singularity part of the same pattern? A kind of cosmic self-preservation? An insistence on coherence? Perhaps consciousness itself is part of this story. We are, as far as we know, the universe's primary way of observing itself. In quantum mechanics, the act of observation is famous for turning a cloud of possibilities into a single, concrete reality. The observer plays a crucial, reality-defining role. Now, in the heart of a black hole, we see a new version of this drama. The nature of the observer, in this case, the infalling matter itself, may determine the ultimate nature of reality at the center. A massless observer, light, experiences a singularity. A massive observer, matter, may not. Could it be that the universe is structured in such a way that its physical laws conspire to create stable, consistent, observable realities, even in the most extreme places? The alternative is a descent into meaningless chaos. And perhaps the universe, at its most fundamental level, abhors meaninglessness even more than it abhors a vacuum. The debate over Kerr's proposal will rage for years. It will be fought in the dense language of tensor calculus and differential geometry. It will involve complex computer simulations of gravitational collapse. It is a battle of giants, waged on a battlefield invisible to the naked eye. But the stakes are not merely academic. They touch upon the deepest questions we can ask. So, we return to the central question, the one we started with. Is the singularity real? The answer, it seems, has changed. It is no longer a simple yes, proven by the towering authority of Penrose's theorem. The answer is now, it depends on your assumptions. It depends on which path you believe is fundamental. It depends on whether you trust the elegant, idealized journey of light or the messy, complicated journey of matter. The question has become more profound. It is not just about the contents of black holes. It is about the nature of physical law and mathematical truth. It asks us to be more careful, more humble in the face of the cosmos. It reminds us that our theories are tools, not gospels. And sometimes, the most revolutionary act is to question the tool you are holding. We are left with a new, and perhaps more beautiful, metaphor. The singularity was a period, a final, unyielding punctuation mark at the end of a cosmic story. It was a statement of finality, an ending. Roy Kerr's challenge transforms that period into something else. Perhaps it is an ellipsis, a pause that hints at more to come, a transition to a new physical regime we do not yet understand. Or perhaps it is a comma, a brief pause in a sentence that continues, governed by laws that are strange and extreme, but never broken. The journey into a black hole may not be a journey to a dead end. It may be a journey to a door to a new kind of physics, a place where matter is transformed under pressures we cannot imagine into something new. A place of becoming, not a place of ending. And what does that mean for you? A creature of stardust looking up at the night sky. It means you live in a universe that might be, in its entirety, a coherent story. A universe that does not contain its own negation. A universe where the laws of nature, the grammar of existence, may be powerful enough to describe every place and every time, without ever descending into the scream of infinity. It does not remove the mystery. In fact, it deepens it. An ending is simple. A transformation is complex. A dead end requires no further questions. A door demands that you ask what lies beyond it. The debate will continue. The mathematics will be checked. The simulations will be run. But the philosophical shift has already occurred. The certainty has been cracked. And in that crack, a new light shines, not from a singularity, but from the humbling realization that we are still at the very beginning of our journey. You are a collection of questions, a vessel of curiosity, living inside the grandest mystery of all. The heart of the black hole remains unseen. But now, for the first time in a long time, it is once again unknown. And in that uncertainty, there is a universe of possibility. The quest for understanding is not over. It has just been given a new, and perhaps endless, horizon. The story does not end. It continues.